So thank you, Bruno, and thank you everyone for attending and for giving me the opportunity to speak. So I'm going to be talking here primarily on the observations of neutron stars as a whole with the LIGO-Virgo-Cagra collaboration and some of the recent results coming more from the population analysis that the collaborations just released. And then I'm going to talk also a little bit about where we might be headed in the coming decade with gravitational wave astronomy as a tool for observing neutron star mergers. So, so here's where we are today and sort of a summary plot from the gravitational wave perspective. The last observing run finished in 2020. Currently, folks are working hard to get the detectors upgraded and ready to go into engineering mode at the end of this year and start taking science data in early 2023. And we've identified in the data roughly 90 compact binary systems, and all the public data and results from these analyses are available, particularly through the GWTC3 catalog and the Gravitational Wave Open Science Center. And you can see that roughly the accumulation of signals follows the effective time volume, which is gigaparsec cube per year, to which a reference neutron star merger would be observable above the background noise of the detector. And the expected search volume for our next observing run will be of roughly 4 times the total search volume to date. So we're anticipating a significant increase in the number of signals available in the coming year. So what have we seen so far? This is our sort of pretty mass diagram that shows here in chronological order the signals that have been recorded. And for this talk, we're mostly interested in the folks that are living down here, like our original 1708-17 and 1904-25. As the black holes have continued to merge, we've had something of a drought of double neutron star mergers, although we've had these black hole neutron star mergers, particularly these two really announced in 2020, the 2 black hole neutron stars and some less significant, but also black hole neutron star candidates that are in the catalog. So, so this is giving us, well, we haven't learned from gravitational waves a significant amount of direct equation of state information from the signals themselves since 2017. We are learning important information about the gravitational wave sky. So I think I would like to highlight some results from a recent LIGO-Virgo-Cagra publication in press, or sorry, in review at VRX. And one of the particularly interesting things that this community might like to know is that we are finding a drop off in the number of intrinsic rate of the number of merging sources right around above 2 solar masses. So we have a rate of mergers which is higher in our canonical neutron star range, and then something of a deficit from say 2 to some higher, 7 or 10, and then the black hole power spectrum, mass spectrum takes over. So we're starting to see structure in the observed masses of compact binaries, which includes structure at the low mass end, as well as intriguing details in the high mass black hole spectrum, which would be also interesting if folks have been contemplating stellar evolution scenarios, but that I won't go into at all today. And I should say, if folks have questions, do feel free to stop me during the talk. So continuing then, let's zoom in a little bit on the candidates observed in gravitational waves, which are neutron stars. And For all of the signals right now, our categorization is primarily driven by the masses observed in the systems. It's difficult to confirm based on the gravitational wave signal alone that the stars could not be black holes. So instead, we rely on classifications coming from, say, this mass gap mass, which is as yet quite broad as an upper bound of a category of merging sources, or a maximum mass inferred for the merging sources coming from the TOV maximum mass of an isolated star with modern equation of state constraints. And so you can read more details here in the population paper. But this mass classification divides the candidate signals into neutron stars, which come from the 2 double neutron star mergers plus the 2 announced black hole mergers, as well as our mystery objects, 1908-14, which is comparable to the remnant mass expected for 1708-17, but based on this analysis, appears more likely to be classified as a black hole. That can change some of the inference right now if you assume otherwise, but it's an outlier from the neutron star population observed in gravitational waves. So we're going to focus then on these double systems, the blue and orange here, and the 2 single neutron stars observed as partners to black hole companions. And based on these mass observations, we can start to compare what we see in gravitational waves to what we had historically seen in the galactic population in radio waves and X-rays. And what we find is, unlike the clear preference in the galactic population for neutron stars of around 1.4 solar masses, we do not see any clear preference. We find a population that,
Go on now. We see the
okay.
fine. Exhaust of one person is a problem.
Okay, good. Okay, so just noticing the chat there. Yeah, so but technical difficulties that I can't address, unfortunately. So yeah, so we see a preference for or a lack of preference for low mass sources. We see more even distributions of masses in the gravitational wave sources, including masses up to around 2 solar masses, and an observed maximum mass in gravitational waves, which is below that observed in all galactic sources. So the colorful peaks here are what we see as the maximum mass in gravitational waves alone. And then the black curve here comes from population modeling of all galactic neutron stars. And the dashed curve here is updated estimates of the maximum mass possible for a neutron star with current multi-messenger estimates of the equation of state. So this picture is showing us that the gravitational wave sky kind of follows the breadth of galactic observations, but with perhaps a less observational preference for the canonical 1.4 solar mass stars when we see the gravitational wave population as a whole. So we're also beginning to estimate the rates of, here I've focused on neutron star black hole and neutron star mergers from the gravitational wave observations of our local universe. And there's a lovely review by Mandel and Brookgarden, which goes through the updated now GWTC3 population results in the context of binary evolution scenarios, kilonova observations, short gamma ray burst observations, and let's see how there's a growing consistent picture of the progenitors of all these observational routes. Okay, so I'll only briefly touch on what we are learning about the direct from the direct impact of neutron-star matter on gravitational waves, primarily to give some reference for where we would be going with this in the future. So our gravitational wave signal, this waveform h of t, is projected onto a gravitational wave detector's sensitivity antenna pattern in a Fourier domain frame. And the model that we use then has a gravitational wave signal, which depends on the sky location and the orientation, the overall chirp mass of the binaries, which I'll define in another slide, the luminosity distance, an overall in spiral frequency fall off coming from the accelerated sweep through frequencies as the system evolves. And primarily, the gravitational wave observations grab their information from the phase evolution. And specifically, what we attempt to extract from the phase evolution of emerging binary system are the component masses, the spin vector relative to the orientation of the binary, and the tidal deformations of the two components. So we saw a lot more detail about tidal deformation in Sebastiano's talk this morning or afternoon. And specifically though, we have a characteristic parameter here coming from the ratio of the mass quadrupole to the external tidal field for an isolated star. And so this is a generally expected to be 0 for black holes with proper gauge treatments, but a factor for neutron stars that depends heavily on the radius. So it's not exactly the radius, as we also have this factor, the love number, which will modify depending on, say, the central condensation of matter within the star, how radius maps to the signature in a gravitational wave signal. But this is what we compare our equation of state predictions to. So of course, as I'm sure you'll hear more about this week, the stars in a compact system are not isolated in a binary system. Their deformations as they merge are not linear. It's not pure quadrupole. However, up to this point, we have been using and testing the tidal deformability as effective descriptors in gravitational models. And Tim has a lovely review here, which goes through how this effective description lets us generate the gravitational wave observation matching. So the specific way this feeds into the phase evolution in the frequency domain of the gravitational wave signal, we have this chirp mass, which is also responsible for the overall amplitude scale of the signal, which is sort of a weighted average of the two stars, or a power weighted average. The mass ratio, often more directly in a dimensionless form for gravitational wave analysis. At the leading order, the spin vectors come in with this effective spin, which is the projection of the mass weighted average of the spin vectors onto the angular momentum of the binary. And we also have the effective tide, mass weighted combination of the individual tidal deformabilities into this characteristic signature of tidal effects on the gravitational wave observations. So what we've seen so far are two signals which gave some meaningful information about this tidal deformability parameter. The first signal, 170817, has a significantly higher signal to noise ratio. So the constraint is tighter, and it generally favored very small values for the tidal deformability parameter compared to predictions from an array of equations of state. The second signal, 190425, had a broader posterior distribution of preferred tidal deformability values, but because the tidal parameter expectation falls off dramatically with the overall mass scale of the system, this was particularly less constraining, especially given information already gained from the first signal, since the range of predictions was very well compatible with all predictions from a range of equations of state. So I'll leave the details of how this equation of state inference has propagated in conjunction with the results from things like the nicer pulse profile timing, as well as other astronomical observations of neutron stars that will be covered in more detail, I'm sure, in the upcoming talks of this week's discussions. But I did want to note one thing before I move on completely, is that for a single event's interpretation, there's correlation within the parameters of a gravitational wave signal. So this is most clear in the correlation between this effective spin parameter and the mass ratio. We see that generally similar to the way we recover chirp mass much better than the component masses, we sort of pull out a coefficient of the frequency expansion of the phase evolution that depends conjointly upon the spin and mass ratio parameters. So there's some degeneracy in what we interpret from a given signal. This also follows through into the interpretation of the tidal deformability, which is part of the motivation of the different spin priors that were used in the analysis of the first gravitational wave signal. So sorry, let me just put up these definitions for those that don't know them off heart. So for example, the interpretation of the tidal deformability for a single signal is shifted to higher values if we assume that the spins will be lower a priori in analyzing the signal. So we can propagate this more directly. For example, if we assume that the gravitational wave signal comes from a population very similar to the neutron stars observed historically in our galaxy, for example, following double-peaked galactic mass observations with spins that are more aligned with the orbital angular momentum, and an assumption about the common equation of state that would describe both stars in the system rather than allowing their component tidal deformabilities to vary independently. For our interpretation of 170817, we shift from the LVK canonical results to something that has more equal masses, smaller spin, and a preference for lambda tilde of around 500, rather than the previous for the same waveform model and the same frequency domain, previous preference for somewhat lower tidal deformability values. The same kind of assumption for, sorry, this is now 1904-25, no longer 1708-17. Shifts, sorry, shifts the interpretation of the system into a 1.4, 1.8 pairing, again with smaller spin, and in this case with smaller tidal deformability with these physically motivated assumptions as to the properties of the stars. So as we go into 04, this kind of analysis is going to affect the way we interpret, or this kind of correlation is going to affect the way we interpret the equation of state information from multiple signals. So this was a LIGO-Virgo simulation of accumulation of signals over time in days from 01, 02, and the 2 parts of 03. This is a simulation of a potential, but of course not guaranteed, additional 170 signals that might be accumulated in a year-long run of 04, starting next year. And so in this expected volume, we may see something like 10 neutron-star, or 10 neutron-star black hole, and 100 or more black hole systems. So once we get a large number of systems, one of the things to note is that the inference of equation of state information has to be done in conjunction with the inference of the mass distribution of the underlying population. So there's a very nice paper by Wysocki et al. That shows this, focused on the impact of 04 on our understanding of equation of state constraint. So with something like 10 signals, we might expect the current uncertainties or comparable uncertainties with effectively 2 signals to shift to somewhat tighter gravitational wave only constraints on the pressure density relationship, and also a much more precise recovery of the mass of the system. But if we do not, if we assume some mass prior which does not match the observed distribution of masses in gravitational wave systems, we'll start to get biases in either the equation of state with a bad assumption about the mass distribution, or in the mass distribution with bad assumptions about the equation of state after around 10 events. So this is something that we're currently very interested in mitigating. So there's work from Daniel Wysocki, as well as Gulom and Talbot in the Astrophysical Journal. So let me wrap up here in the last few minutes with a short note about where we might be going in the future from the current generation of observatories, which over, say, the next 5 years, we anticipate trying to press our sensitivity downwards to this blue A+ curve, after which we'll be close to the limitations of the current installation facilities, here illustrated by the Voyager curve here in orange. So there are proposals now in place to build next generation facilities like the Einstein telescope, which has had excellent funding news recently, as well as a US-led project which is called Cosmic Explorer. And the goal would be to shift from the current generation of facilities into the next generation over the coming decade or so. Similarly, at the same time, we're going to be having additional electromagnetic follow-up capabilities, or potentially EM survey merger identification through kilonova alerts that would allow us to then go back to the gravitational wave signals or data to find counterpart signals. So with a next generation facility, the precision with which we recover the individual component parameters becomes meaningful. So you start to get independently measured lambda1 and lambda2, rather than only a single joint lambda1, lambda2, which would be sort of the thickness of this ellipse between the two. We would actually have individually resolved component properties from the two stars in the system, and a quite significantly more precise joint lambda tilde tidal deformability. So this is coming from proposed abilities of future detectors to vastly improve the precision which a given signal is observed. So this was 2015's observation of the first black hole merger. This is what it would look like in advanced LIGO design sensitivity, and this yellow is an unfiltered projection of what would be read out of a Cosmic Explorer observatory for the same signal. The cosmic reach would allow next generation facilities like Einstein telescope and Cosmic Explorer to observe most of the neutron-star mergers in the universe and extend past the projected star formation rate driven projections for black holes distributed through redshift into primordial or first generation stars remnants. So that's allowing us to really get a much more well-resolved handle on the population properties. And so the goal here is that we would be predicting per year with the kind of sensitivity that third generation telescopes give us, or sorry, next generation gravitational wave observatories give us, something like thousands of neutron-star mergers per year, identification of 80% of all mergers within nearby universe, and hundreds with unique properties like high precision radii or early warning for mergers. The last thing I wanted to note was that one of the science goals of next generation facilities is post-merger gravitational waves, which are expected at frequencies. This is a projected population averaged sensitivity with two different equations of state. These post-merger sensitivities would be highest around 2000 to 3000 hertz. This is actually the only science target where a 20-kilometer Cosmic Explorer detector can be better than a 40-kilometer Cosmic Explorer detector, given the capabilities of tuning a lower arm length to target a specific frequency range. So this is something that's going to be interesting to contemplate what unique information is accessible from this kind of 100 or so post-mergers per year projected with future capabilities. So I'll stop there. I'd like to, however, invite everyone to join the Cosmic Explorer Consortium at cosmicexplorer.org. This is a nascent collaborative network to try and engage folks with the development of the science case and data release policies of the next generation gravitational wave observatory on the US side. It's by no means exclusive. The consortium itself does not have specific science responsibilities. There would be subgroups within the consortium for that. So please join it. Right now it's a mailing list and an occasional science call to advertise interesting and relevant work for folks interested in next generation gravitational wave astronomy. So I think I'm out of time.
Yes.
So I'll leave it here, sorry.